So apparently now we should stay on topic as opposed to entertain people. But so what I'm going to move now is Db2 architecture. I had planned originally for an hour, so I was going to talk about BLU, and Chris said, oh, you have an hour and a half, so I kind of throw in about a 30-minute sort of front matter that is BLU and row. And the goal will be about an hour and a half, and it's really up to you based on how many questions you guys ask. Usual disclaimers, but this is mostly architecture, so mostly not relevant, except for maybe a couple things on BLU. So I'm going to start with the overview. This is a basic walkthrough of basic operations, both row and sort of in some cases columnar. At the very end of this, after my last slide, there's another 30 plus slides of bonus material on row organized. At Charlotte, we did 4 hours of architecture talk, where presentation 1 was this, plus this bonus material. So this is kind of 30 minutes, and then this is 30 minutes I'm not going to get to because we won't have time. We did an hour of BLU, an hour of pure scale, and another hour of like SMS table spaces, DMS table spaces, memory architecture. So those presentations will actually probably appear in the hybrid data management community sometime over the summer when I have a day I'm not super busy. So for anybody who uses DB2, what you know from single node is, you've got all the cores, you've got all your clients coming in. Inside the DB2 server, you get a coordinator agent. If you're running simple OLTP, that's probably the guy who's doing the work. If you're doing a parallel, table scan, query, index scan, anything large, you will get parallel subagents to help you out and parallelize the work, or even parallel insert. You've got a package cache, you've got lock lists, buffer pools, log buffers. Your log buffers have log readers and writers who get things out to disk. Your buffer pool have prefetchers or I/O servers and page cleaners pulling in and putting things out to disk. So that's DB2 in a nutshell. There are a few things that we exploit. So number one is parallelism. We have done this for decades now. Supporting for multi-core both inter and intra-parallelism, so between nodes and within a node. The cost-based query optimizer, we parallel in SQL, we parallelize our utilities. We exploit multiple cores. We are threaded on all our operating systems. This one I kind of laugh at because this is a slide that has been enhanced every release for the past I've been with DB2 27 years, but 64-bit support. It's like, yeah, okay, that's pretty well. I think we actually don't even have a 32-bit server anymore, right? So everything is 64-bit now, but it's still there. I/O buffering, caching, the ability to prefetch and push out multiple buffer pools, right? And then under the I/O subsystem, the ability to do asynchronous, to automatically stripe, do parallel, big block I/O, scatter, gather. Some of these actually, for who is still running on HDD versus running on SSD? Anybody still on hard disk drives? It's actually, I guess in an enterprise world, that's not that surprising, but we still have customers on both. So, when I talk about the parallel I/O stuff, you have both, yeah. And sometimes it's old databases versus new. Sometimes it's the most hottest, most important data versus not. And sometimes it's just cost. So that's what the single one looks like. And if you run DPF for the database partitioning feature, or we're starting to call it MPP a lot more because it's what most of our competitors call it, you take what we had on the previous page and you basically split it up with shared nothing where each owns some partition of the data. Right? So this is a shared nothing configuration, but each single one is very much like what you saw in the previous. Wherever you connect gets the coordinator. If he needs to talk to the other nodes, he gets parallel subagents on those other nodes to help do the work. And again, most things run in parallel across the cluster. Queries, insert, update, delete, your utilities can all run in parallel. Shared nothing configuration. The next one we support is pure scale. So again, you see the same architecture for the base core engine, but what you have is, yes, the logs are still per member, but now you have shared data and all the coordination for multiple members to access the data. And in addition to that, you have primary and secondary CFs, which are used for part of the coordination and also passing data between them. Generally over a high-speed interconnect, and I think none of you said you read pure scale, so I'll skip over that quickly. Row-organized query processing. So what I'm going to do here is, using the same picture, I'm going to walk through what a simple query looks like and the different things that end up interacting. So here we're doing a select column 1 from table 1 where column 2 equals 5. And this one is row organized. So at the beginning, the statement is sent over the network from the client. It is compiled and optimized. And that resulting compilation gives us what we call a statement or sections that go in the package cache. And it is stored there and can actually be reused by other dynamic SQL that's running that. And then you will start to execute it. And in this case, you go back to your coordinator agent. And because here we're assuming there's no index, it's going to actually kick off a bunch of parallel table scans. Those parallel agents tell the prefetchers to start reading ahead, because you don't want the agents doing I/O. Even the agents, you want them to run, find the page, find the page. And the other thing is, because you kick it off to the prefetchers, they can actually do big block I/O. Right? The agent would have read a page at a time, which is inefficient. These guys will do prefetch size ahead and do it in extent chunks. So now they actually bring this into the buffer pool, your prefetchers. As these agents come in and ask for the page, they're going to grab one of the pages. Assuming it's compressed, they're going to decompress what they need to, and they're going to scan the page a row at a time, saying, is C2 equal to 5? If the answer is yes, it's going to grab C1 because it's row-based, so it's already sitting at a row with both C1 and C2, and go put it in the result set. And it basically repeats that through every page for all of the things, and sends the result back to the client. Right? So in row-based, your prefetching kicks in, but as you are evaluating the row, you can return back C1. Now, the thing you'll notice is that between all of the parallel subagents, you touched every single data page in this object, right? Because it was a table scan, because in this case we said there was no index. And so, if your whole table was 100 terabytes, you just read 100 terabytes of data to return some number of C5 or C2 equals 5 columns. So how would that work in BLU? And when we get to the BLU thing, you'll realize I oversimplified this a lot, but we'll skip those initial steps, right? So we're going to just start with it's already executing. So what it does now is, we know that we're trying to look for C2 equals 5, so the only thing it's going to scan is the C2 column, right? It's not going to touch columns 1, columns 10, columns 50, any other column at this point. What it's going to scan in full is C2, and that could be 1% of your data. That could be 0.5% of your data. Maybe it's 50%, but that probably means you only have 2 columns, right? But there's a good chance it's a very small subset of your data, and that's all you're reading. So you may be reading 1/30th of the data, 1/10th of the data at this point. Again, it's going to send off the prefetchers, because you'll see later on, and George talked about this, is pages and extents only have 1 column. So we can still do the same great prefetching, but again, only against C2. Those pages are brought in, and as I said, they scanned. And another part that's different is, rather than decompressing all of those columns, we instead compress 5, or I'll say encode 5, and compare encoded values, right? So again, you're not unencoding everything. You're only going to end up having to deal with the ones that match. So here, now you're going through your page and you find your matches based on the encoded data. And all you're going to do is remember which TSNs. Think of it like a row ID or a, in row-based. Remember the TSNs that matched, right? So again, maybe there's 1, maybe there's 100, right? Then what you do is, once you've got your whole list of TSNs at the end, you go through those, and just for those values do you ask for the C1 column, right? And maybe you have good clustering, so you pull in a few pages. Maybe there's 100 rows with 100 different pages you have to access. But now you scanned all of one column, and then maybe you're getting, say, 100 pages of some other column, right? So what you see, and it's one of the reasons why BLU can be much, much faster, is the amount of I/O was much less. And even if you're 100% in memory, the amount of page fixing can be much less, right? So now you, based on those TSNs, you grab those rows, you return them the same way you would have, and with the exact same answer set as you would have, but potentially with a lot less I/O. And potentially doing very little decompression. Because at no point did you ever actually decompress C2 because you just wanted the TSN, right? You never even had to do the matches. And then send to client. So a few things. I ignored the existence of a synopsis table. And we'll talk more about that later of how that affects things. So let's compare the internals for columnar storage versus row storage. So this is logically in your mind how you think you have a table, right? You've got a name column. I'm going to say that's age, address, city, state, postal zip code, right? And if you're in row-based, the pages are going to split that way. And the extents, so let's just, are going to split. Sorry, now let's switch to BLU. The pages are going to split this way, and as are your extents are going to be the sequential pages. Now, if you look at columnar, your pages are going to split per column, as are your extents. So again, you will get one extent that has, by default, 4 pages of names, 4 pages of ages, 4 pages of addresses. And another part where BLU is strong is these are much more likely to compress together because they are all text things and there's more likely the commonality. And maybe it's not as obvious here, but when you go look at the age, these are going to compress super well because they're all really a number from like 0 to 100, right? So, with a very small number of bits, you can actually compress this, right? Address, you'll get a little bit. But again, city, you might get a bunch. And in here, there's really only like 50 values. So, you're talking 1, 2, 4, 8, 8 bits to be able to do that, right? And again, here you'll probably get some because again, it's not a giant number, it's a 5-digit number, right? So much better compression because you're comparing and trying to compress data that is much more alike, right? As opposed to when you looked at this one, right? On a page, you had a lot larger variety of data. Now, one of the things I will mention is row-based will actually compress across columns, where columnar only does it within a column, right? So, if you had Los Angeles, California, this would be compressed together in row, where they are compressed separately in columnar. Extents, this assumes extent size 2, where things are chunked into extents. So each extent contains only one column. That becomes important if you have super small tables. Row ID and TSNs it's tuple sequence number. So like this would be tuple 0, this is 1, this is 2. We have a page map index so that if you were down here matching some guy named or girl named Pamela Funk, she's tuple 5. So we have a page map index that can then find tuple 5 here because although it's on the first page here, and it's probably on the first page here, maybe when it comes to the address, it's on the 5th page or the 10th page. It has to know how to find that. And typically, because of all the compression reasons I mentioned, columnar tables get better compression and are much smaller than row-based tables. The one exception, and we'll talk about it a bit in some of the best practices, is if you have really small tables, if you only had one row, you're using one extent per column, right? So in the very small case, you can have overhead of a lot of blank space. Any questions on that quick layout? And like I said, this is the stuff where stop me if there's something you have questions on. So row organized insert processing. So we already talked about how to do selects. We'll now talk about how inserts are done. So same thing as before, you get to the point that you start with the access plan. So the first thing an agent needs to do in row organized is figure out where it needs to put that row. So the first thing it does is it searches for a page large enough in the table to hold the row. And we have these things called free space control records that we search. They're every 500 pages. We can jump forward. The back matter that I'm not going to get into for row specific goes into detail of all the search algorithms and how to tune them. So now you found a page and it's been read into the buffer pool, so it's that little squiggly line there. So now we actually locally latch this page X, and we also get an X lock on the row. So now we have a lock for that row, and at this point the same agent will then write into the log buffer the fact that he's going to do this insert. So he's going to write the new redo data, just in case you crash, to be able to redo it, describing how to redo it and undo it if you choose to roll back. You then do this action or whatever this insert is. So let's say you inserted the value 5 into this page because you have space for it. And then you actually will mark this page dirty because you changed it. If it was already dirty, it just stays dirty. If it was clean, you're the guy who marks it dirty. And you send success to the client. Right? So far what you've seen is log buffer to memory, data page updated in memory, nothing getting hardened to disk. And the client is told success. So just keep in mind at this point there has not been a commit issue. This is just insert, and there may be subsequent ones. Now this contrasts this to the column organized insert, and let's assume we're doing a single row insert. Same first 4 steps, but now you actually have to assume it's a 4-column table. You have to bring in 4 pages to write the data to. Not just one, because you've got to split it, column 1, column 2, column 3, and column 4, right? And BLU is append only, right? So if you do an insert, it will always go at the end of, I'm going to say the table, but it's really a range of the table because we have multiple insert ranges. And so these pages are found, brought in, but now the same thing. Sorry, you require the X lock. But now for each column, you got to write 4 separate log records. You got to do these 4 separate updates. And 4 separate pages are marked dirty, even just for 1 row inserts. Pages are inserted into success to client. And I'll say this is an oversimplification for a number of reasons, because there's also synopsis maintenance. And there's actually, we buffer sort of into memory first and then flush at a different time. But I'll get that into too much detail. But the goal here is to show that for a basic insert, you might do 4 times the work or n times the work, which is why single row inserts are slower. And it's why when I talked about some of the features, we're looking at a trickle feed where they'll go in almost row-like to avoid some of this overhead to begin with. And then send success to the client. Now, what you might be thinking is, I pointed out that 2 things were done to memory, the log and the data page, or the data pages for columnar. Why do we do this, and why was nothing written to disk? And the answer is we really try to batch things and amortize the cost of anything as much as possible. So if you're going to do 50 inserts, those 50 inserts may all go into the same page. Or even if you do 50 inserts and somebody else is in parallel doing 50 inserts, there are still updates being done to the same page that can be shared, and only 1 dirtying of the page, and therefore only potentially 1 I/O, right? And the other key thing is the transaction is not yet committed, right? So if we were to crash, if we have no copy of the log nor of the page on disk, that's fine, because we did not tell you that, yes, we are done. We told you that, yes, we understand you sent this to us, and when you commit it, that is when you get the guarantee of you will not lose that, right? So the fact you haven't committed also means they can both stay in memory. We just need to be able to do undo or redo as required. So the question now becomes, when do we need to write things to disk for both the log record and the dirty page? So the answer to that is commit, because that is the point that we give a guarantee. So when the commit comes across, the agent will write a commit log record to the buffer for that transaction. And then the agent will actually tell the logger he needs that commit to be on disk, because that guarantees if we were to crash that we see the commit on disk. And the logger is actually fairly active, so the gets around to it is pretty quick. Will come through and see that it needs up to here written to disk. He will write that to disk, And he will post back all agents, including ours, to say up to here is physically on disk, right? And what you'll notice is I've only talked about the log record going to disk, not the data page. So at that point, we can release all the locks we got in the earlier step and send success to the client. So the key here is all that is written at commit time is the log records. And the reason why you want the log records to be what written is those are sequential. So, if you had 25 inserts in here and then a commit, it's potentially just one IO to get no matter how large your transaction is on disk. Whereas if you had 25 inserts to 25 different pages and 25 index pages, if you required the data to be on disk, you would have had to do 25 random IOs. So commit is guaranteed by forcing the logs to disk. And then that, of course, leads to your question is, okay, well, you had a dirty page. When does that hit disk? And how am I guaranteed that my data is not lost if the power goes off? So let's talk about the case of the power going off, so crash recovery. So here the client connects. This will kick off crash recovery. The agent, when he comes in, says the database is inconsistent, because if we come down consistent, we write a flag to say it's consistent and no recovery is needed. So what he then does is he starts something that we call redo, right? So we have a starting point based on what is the oldest thing buffered and what is the oldest transaction that is not yet committed. And we start to redo logs from that point. And so now what he's doing is he reads every log record and says, okay, this is an insert. It says I inserted to page 50 the value 10, right? Or maybe the value 10, Smith, something. So at that point, he actually replays it by fixing that page and says, is this done yet? And he can do an LSN comparison. And if it's already done, he doesn't need to do it again. If it's not done, he just replays the log record and redoes the insert. And if he has to redo the insert, he marks it dirty to say the page is dirty in the buffer pool. And he reads through all of your logs that you wrote, including the one for those last inserts, and redoes those inserts. Now, once he gets to the end of the logs, he has rebuilt what we call the transaction table. So anything that committed along the way got pulled out of the transaction table. So if you did an insert and a commit, that got redone and then pulled out of the transaction table to say that it's committed. Now, if you do an insert and you didn't get to the commit point, it's going to be sitting in the transaction table as an in-flight transaction. And it's going to look just like you did at runtime. And if at runtime you had issued a rollback to everyone, that's essentially what happens in the undo phase, is everything that was in flight, we did not tell you it committed, and therefore we must roll it back, right, to return you to a consistent point. So then in the undo phase, for every in-flight transaction, we just basically process undo for every one of those and return you to a consistent state. During that undo, you will actually log the undo action. So if you had an insert and you needed to roll it back, you will log a undo insert log record. So essentially more or less a delete. Those will not do any locking, but they will, drive your prefetch. We will redo, and once you are done, we will actually open up your database and say, here you go, you are crash recovered. This is very similar to how roll forward works, right? You would roll forward and redo all the log records. Whatever was in flight at the point that you stop at is undo to return you to consistency. Does this make sense? Have people seen this before? Okay, so now what about that dirty page, and when does it get written to disk? So if you have multiple agents inserting or updating or deleting, right, multiple people can dirty the same page, or they can dirty this, different pages. And let's assume that you had your cleaners tied up for some reason. In absolute worst case, and this should never actually happen in a production database, and if it ever does, something's configured wrong and you should fix it. You would end up with an agent trying to bring in a new page on the next insert. When he gets there, he's going to find that the buffer pool's all dirty and he can't bring in a new page. So he's going to have to write one of these pages to disk, right? And this ends up being an agent synchronous write. And like I said, if you ever see this, this is bad. When he writes this page to disk, he actually needs to make sure that the log records that have the dirtiness of the page, so let's say it was inserted by 4 guys, the last insert, we need to make sure that that log record is totally on disk, as are the previous ones. And the reason for that is if you were to crash, you need to be able to undo that. So now he writes this page to disk. He writes the log to disk, comes back, told it's done. He will now come in, write the page to disk, and victimize the page. So once it's clean clean in the buffer pool, because he's put a copy on disk, he can actually get rid of the page out of the buffer pool. He can bring in his new copy and update it, right? And as you can see, based on, compared to my simple example, this is like 7 extra steps with 2 extra IOs, right? Don't want this happening, right? But this is worst case of somehow nobody's cleaning your buffer pool. So what actually is meant to clean your buffer pool are your page cleaners, right? And they write it for multiple reasons. One is because it's in the background, you don't get the latency to the agent to do the work. The other one is they can do more efficient batch I/O, right? And because of that, they can put multiple IOs out to the operating system at once, and the operating system can also coalesce things, right? So if you send out IOs where 4 of them are to the same area, the OS can actually group those together and do them as one IO. So you get better IO. Would have sworn I had one more slide to this. The one thing I will mention here, and it's probably in the follow-on deck, is who here runs OLTP in general reporting workloads? Anyone, or is it all warehousing? So as of, and it's so long ago, I'm going to claim it's 8 dot something. We have something called alternate page cleaning, and that actually, these guys are way more proactive, and I strongly recommend for anybody running OLTP to turn on alternate page cleaning. It is actually the default in BLU also. The only reason it's not the default everywhere is there's some warehousing cases in row that we know that the old version can actually perform better. But for OLTP, definitely turn it on. And BLU, it's workload analytics is also on by default. And that's probably in the back matter of the deck. Yeah, I said it was so long ago that I'm going to say 2003. Any questions on that? That was sort of my quick, a little bit of row-based stuff, just to have it not all be blue for people who weren't all blue. No? Okay. Made all sense? Made most sense? Made some sense? Yep. Okay. So let's talk about BLU. So back to the who was, just so I remember, who's touched BLU, played with BLU. Okay, so about half the room. For the people not on BLU, feel free to tell me to go slower if I need to, because it's probably less review than some of the previous stuff. So what is BLU Acceleration? So it's the next generation of database for analytics. Some of the key points are performance improvements, storage savings, so we talked about compression, and simplicity, so we'll talk about some of the load and go benefits. It's seamlessly integrated, so it's built directly into Db2. It shipped, I'm going to say, in 2012, so it's been 7+ years now. Exact same SQL, you run it, it's just what you create your database against, and like lobs, we're filling some gaps between regular and BLU tables. It's very optimized for hardware, so memory, CPU, and even I/O, and it's available in Db2 on-prem, which I will just call Db2, Db2W or Db2 warehouse on cloud, and IaaS. So these 3 are all the same containerized, but in you install on cloud and on the appliance. And then this is Db2 on-prem, which is also available as a container, but different licensing model. This is basically the big one marketing chart I have at the beginning, showing that across a variety of workloads, it's for somewhere between a 3 times and I think this is a 70 times speed up. And if you average these workloads, it's almost 37 times faster, right? And these are specific analytics workloads; they're not OLTP, but examples of some of the speed ups you could have, especially on specific queries. And there are cases queries can be 1,000 times faster. And when I talked about the simple select case, you can understand why, because you might do 1,000 times less I/O if you have lots of columns and you're avoiding big varchars and just doing things, especially on integers. It's super small. So here's an example where we showed what the original table looked like. The blue is when you actually compress with row-based compression, which is, still a third the size, or, 2/3 to a third the size, depending on the example. And then even how much smaller it became with blue because of putting columns with similar type of data all on the same pages, being able to do minus encoding. It can still be much, much smaller. And this also, like I said, really is part of why you get a speed up, is you do much less I/O, both because you read less columns, but also because each column is smaller. And you get more memory efficiency too. So lots of benefits from that. Super easy. So the goal of BLU Acceleration, and I won't claim we're 100% there on everything, but is essentially that you create the table and you load the data, and that can either be through ET type stuff or, I'll call it the uppercase load utility. And then you're done, right? There's a lot more automation here where run stats automatically runs, right? This is one of the reasons things like the ML optimizer, so you don't have to worry about column group stats, that the ML optimizer will take care of the cardinalities. All of that, such you load your data, you get your synopsis, you don't worry about indexing, basically the load and go philosophy, as opposed to what do you need to create? Do you need materialized views? Do you need indexes? Do you need to tune, right? And especially with DB2 Warehouse, there's a lot more auto-configure and auto-tuning specifically for warehouse workloads and specifically for BLU to make that happen, and things like automatic WLM and adaptive workload management and all of that built in. So will your benefit or workload benefit from BLU? So the probably case, or the it depends if you've ever had Bernie present, analytical workloads, data marts. If you have lots of grouping, aggregation, range, joins, it's used in our SAP Business Warehouse, Netezza migration, star and snowflake schema, right? Especially queries if you only touch a subset of your columns, right? If most of the time you are joining on a few integers, right, and then occasionally go after, other columns associated with it, much faster because you're not reading everything, you are reading a subset. Where not to use it? Probably not. I would just say not for OLTP at this point. We have an HTAP strategy that we're looking at to merge them. I put a star on insert updates for a few rows, right? We are putting enhancements in upcoming releases to make that better. If all you ever do is a select star, columnar is probably not going to help you. And there's certain things like XML and pure scale, and those are not with BLU yet. So lobs used to be on this list, now that's off, right? But we are closing some of those gaps. Any questions on this one for the people, especially the people not using BLU? Core concepts, and I'll get into a lot more detail for these, but dynamic in memory. So this is saying that we keep as much in memory as possible, but you're not required to keep 100% in memory, right? Actionable compression. So I talked about this in the simple select case, where you do not necessarily need to decompress to do things like comparisons, inequalities, and likes, right? So you can do actions on the compressed data, making it much faster. Parallel vector processing, so the ability to exploit hardware and SIMD. And data skipping. So, many people used to use range partitioning in row warehouses so that if there were 10 partitioned, maybe something was on a date, and you would only have to do something against one partition because that's the only place that date existed. Through the synopsis, that is automatically built and maintained. So that's part of the load and go philosophy, is through the synopsis we do that. You do not need to range partition yourself and do that by hand. These ones I'll go through really quickly, but if you want to create a database for BLU Acceleration, really you can either take the DB2 Warehouse container, or you can set DB2 Workload Analytics. This will automatically reconfigure for an analytics workload. And you create your database, and it will automatically be, what we'll call a, analytics or BLU database. If you want to add it to an existing database, you can, set workload equals analytics and run auto configure to reconfigure some of the settings. This isn't required, but it's strongly, strongly recommended because, you want parallelism across your queries. You want to turn on inter-query parallelism. You want to change your extent sizes. So what does workload analytics do? Number one is it sets the default table org to column. So from that point on, every time you say create table, if you don't specify, you get a column or table. Because it's an analytics workload, we want your page size to be big, so you put as many rows on a page and get as much page compression as possible. But because of that, we also drop the default extent size. So the reverse in non-workload analytics is actually 4K page and 32 pages. So the whole extent is the same size. It's just the which is more important is reversed. Default degree ini. So like that Kiwi theory. Kill it with iron. You want to parallelize your queries. Catalog cache is higher. Sort heap and thresh heap are set higher. So you're doing a analytics workload as opposed to us guessing what type of workload. So more sort heap. Your util heap is higher. Your WLM stuff is automatically set up. Auto table maintenance is set up. So this is key because this is also part of the load and go, right? We'll automatically create dictionaries. We'll automatically groom in the background. We'll automatically reclaim, right? So set that up. And there is a bunch more. So like I mentioned, it uses a new page cleaning algorithm. I believe it defaults to, even if you have an existing database, it defaults to Unicode, right? So it also defaults to a lot of our future directions, right? So in our recommended configs.
So the automatic table maintenance and automatic, what's the impact of that on your environment?
You don't have to worry about it.
Like things automatic, like running when we don't know. So what would be the impact of that?
Well, so I mean, so it will not affect your concurrency because the things that are automatic are concurrent and meant to run in the background. But what it means is you don't have to worry about, let's say you have a blue table and you've been inserting into it, but then you delete all of last month's data or 2 years ago data, right? It will automatically free up those extents in the background, right? So, and all of that's completely online. So is there some CPU used? Yes. But you don't have to worry about it, right? It happens in, I don't know any DBAs who have turned it off. I'm not saying it's free because if you are looping through and reclaim, yeah, it costs some CPU, but they're small transactions, so we don't hold up log. They're done online, right? But yes, there is some CPU overhead to make it happen, and same with groom. So if you create a table, you can either say organized by column, or if the default org equals column, it will happen automatically. If you've set this and you want one that's row, you say organized by row. So fairly simple. And the other thing to mention is columnar tables are always compressed by default. And actually, I should take out the by default because they're always compressed. You can't really turn it off. Unlike row-based, you can either have them compressed or not compressed or different levels. We pretty much went through this in much more detail in the front matter, right? So, the key is you've got TSNs. You've got things that are split by pages per columns and actually per extent. So how can you tell if you have a table what it is? You can select table org. C means columnar and R means a row. They actually made sense for once, so that's good. That probably doesn't in any other language than English, so I apologize. But and then the note is for columnar, it doesn't comment on compression because the answer is just yes, it is compressed. Whereas here you can have no, and I think it's static, and I can't remember what A stands for something. The synopsis table, so data skipping. So the key is when you create a table, any of the columns other than lobs and long varchars that are, I can't remember some size, it's over like 256 bytes, it's something pretty small, 4K, you will get for that row, you basically, what the synopsis table does is between TSN range 1 and TSN range 2, and as of the latest code, this should almost always be 1024. For every column in the table, we say what is the min and max in that range, right? So in the first 1024 TSNs in the table, the dates go from 2005 to 2006, right? So now what happens is if you're running a query that's based on the date and you ask for a date in 2005, it goes, yes, I have to look at the first 10, 24 rows, but oh look, somehow this data is actually sequential and mostly going up, therefore I don't have to look at any of the rest, right? So this is kind of like some of the benefits you get from range partitioning without having to do it. You may find that for another column it might be age, right? And unless somehow you sorted it based on age, you'll find that the range is actually, almost from super low to super high, and those you will not get a benefit of for the Synopsys. Today, as a user, you don't get to choose what's in the Synopsys or not. Those are things where we are working on, self-tuning and algorithms to basically leave things out of the Synopsys that we're not getting value, or even reorder your data so that we're almost in sort of sets of things so that you get even better Synopsys usage across multiple columns. Who's used MDC? Right? So the way MDC kind of says I have 2 dimensions and I'm going to cluster across it, it's sort of doing something similar like that to the data within the table by reorging it so that your Synopsys can work in multiple dimensions.
That Synopsys table has multiple columns in it as well, right? The TSN
yes.
min and max will have maybe 5 or 6 or whatever.
Right. For this TSN, it will have, for every single column, it will have the min and the max for anything other than lobs and larger varchars. Right. And usually what happens is it works very well on a few columns, and then some of the columns are more random, right? Like age, for example.
So you're saying with Synopsys table, you don't need range partitioning?
So that is one of the reasons why BLU does not support range partitioning, is because the Synopsys table gets that same benefit of partition elimination. And it actually does it at a much smaller granularity. So what do you see in the catalogs for the Synopsys table? You see sysibm.synopsys and then some magic number for uniqueness. And then I can't remember if it's all or some subset of the column name, just so you can match it. And it is also a columnar table, right? So the Synopsys table itself will compress and do things like that. So also good to know. I mentioned this briefly, but the other thing that's automatically created is the page map index. And you'll see this as, again, SQL, some magic thing. And it's a column group plus a start TSN, and it's called the column or page map. I'm going to just say that stands for map. And what this does is per column group, i.e. each column right now is its own column group, you get a start TSN of what's on that page, essentially. So if you are looking for, when I was talking about the example where you had gone through the select statement, you come up with a list of TSNs, and now you want to find column 1, right? You're basically going to say, for column 1, I want start TSN 50, and I want TSN 100, and then you search through that and go, well, that's really on page 10, and that's really on page 25, right? And that map allows you to find where the associated columns for everything associated to a TSN.
Hey, Keri, without the range, without the partitioning range, you can't drop like a whole range of things.
Right.
Because that's what we do. Like in our warehouses, we have a rolling 17 months of data we keep, but at the 18th, I drop one and I don't have to do anything. All of a sudden,
right.
Detach the partition and drop it, it's gone.
Right, and that's why, we're debating where range partitioning is on the priority list, because historically it's been used for roll in and roll out. Right. At which point,
that's the most critical.
Right. At which point, BLU is actually much better for roll in for row based, because you can do it online, right? Deletes are actually much faster, right? Because you are only changing a bitmap index essentially of
billion rows in one calendar
right.
year.
So
that's a lot of
it's still but it is still
the other way,
right.
Detaching and dropping it the other
right.
way. I'm physically deleting
right.
it in the background, which a lot of things are moving.
Right.
Why do we want partition elimination for tables which have billions and billions of rows?
So that's where you should. So partition elimination for queries you should get from the Synopsys table, right? Your Synopsys should tell you you never have to touch that, right? The case that it doesn't fix is you will still do more logging on deletes and inserts, even with reduced logging. And the other case it doesn't fix is actually when you roll out a table, a lot of people actually keep what it rolls out. And they'll use that and maybe actually attach it to a different table of history. That is the one I have no answer to, as opposed to at least we're better. So that is why it is something that's still on.
Just a curiosity question, because
And so that latter one is why it is definitely still on the the roadmap, but it's some of those other reasons why it's not as high as a priority as it was in Row. And the other one being, a lot of BLU customers are starting on MPP, right? So therefore the divide and conquer for utilities and stuff you already get from the MPP version. But yeah, so like I said, the case we don't is yes, some of the deletes and inserts can be larger, especially for logging or slower, and then definitely the keeping what you threw away or rolled out and attaching it somewhere else for like archiving purposes or historical purposes. So it is still on the roadmap for that reason. Execution flow. So one of the key things I talked about is the evaluator change. Basically say, the operations you're doing, much like if you saw sections and look at explain. And again, parallelism. Multiple subagents doing the exact same thing in parallel. And we use a straw model to distribute the TSN ranges. And one of the things I don't think I have a slide on is we basically skip in strides. So based on how much memory you need to process each set, we decide on a stride size, and then the first guy gets 1024, and the next guy gets the next 1024, and the next guy gets the next 1024. And when they finish up, they come and ask for the next one. Right? So that's kind of everybody takes a sip, and then when you're done, you come and take another sip. Processing query order. So, the first thing is we use the synopsis scan to skip as many tuples and as much as we can. Right? Then we try to do predicates on much of the compressed data as possible. So like I said, you will encode what's coming in and compare it to compressed data. Joins and group bys, right? So the expensive operations try to get them going on as minimum number of rows. And then, after you decode, will you do complex expressions, all the math, all the aggregation, right? So, try to do the things that get rid of the most data and are as cheap as possible, and the more expensive things you do later. So this is just a rough order of how we try to optimize things. Another term you'll hear when people talk about BLU is late materialization. And you saw this again in the query that I used as an example that, when you were selecting some number of columns with a predicate, you basically keep storing row IDs, you don't keep storing data, right? And then only at the end, when you have a subset of row IDs, do you actually start going off after column 1, column 2, and column 3. Right? And that is called late materialization, and it really reduces the amount of I/O. And it often reduces also the amount of temping and the amount of memory used at runtime. And this is all accounted for in the optimizer's cost model. So it's one of the key things of the secret sauce of what makes BLU faster. Here's just an example where we can't materialize everything at the very end, but we can sort of do piecemeal as we go up. So here you were doing a join, you're doing it based on year, you don't have to scan the date till later, right? You don't have to grab customer keys till later, right? Just push things and delay as much work as you can till later when you hope it's less work, right? Because if you got to go get a column for 1,000 rows, it's much more expensive than getting it later when you're getting it for 50 rows. How did I end up with... I'm not going to claim why slide 2 is first. Hopefully nobody notices, but I just said it out loud, so that just wrecked that. Actionable compression. So we talked about this earlier. It is worth mentioning multiple times because it is basically, one of the key parts to performance is predicates like equals, less than, greater than, betweens, and even I'll say some likes, like a like in the middle, no, like a like wildcards. But like, Smith star, those types of things can be, you can take what's coming in, compress it, and then do comparisons. Even some of the group by and join processing will actually encode data and use on-the-fly encoding to compress it in memory and do as much on the compressed as possible. And avoiding decompression, significant, if you are doing 1 million comparisons and you encode once versus decoding 1 million times, think of how much faster that is. That row tables is not actionable. And I mean, part of it is because you will actually compress across columns, right? So if you're compressing like state and zip code, right, it's much harder to do that. You get 1 dictionary per column, right? And that makes sense because you are compressing, within a column. In addition to column level dictionaries, there are also page level dictionaries. So much like row, once you've compressed something based on a column level dictionary, you may find that within a page you can even get better compression by compressing data for that page. And a good example is you had dates, and so you had 2008 and 9 and 10, and now some stuff with 11's coming in, right? Maybe you can't compress that as well because it's not in the dictionary because it's new, but you can still get some page level compression. So what type of compression do we do? So the first one we do is what we call frequency or pure dictionary encoding. And this is any value that's repeated. You basically encode it for less bits. And one of the key things with BLU is within the same column, we can actually have some things that are encoded by 1 bit and some things that are encoded in this case by 3 and in this case some things by 6, right? And this means California and New York have, and I'm going to quiz you, what percentage of the total US population? Someone help me out. Some high number. Don't quote me on that, I could be wrong. But let's say it's 30%, right? It means 30% are using only 1 bit rather than 6. And this Alaska one, I'm going to go out on a limb and say it's less than 1%. Right? You got 50 states, and I'm just going to assume it's less than 1%. So, it's got 6 bits. So you are going to find you get much better compression because the hot ones are using less bits. In addition to those types, we also support what we call prefixing encoding. And rather than having to match the whole key for a char type column or character column, you only have to match the first ones. So if within a character column you put MAR for March and then 01, and I have never figured out why people do this for dates, but people do it all the time, or product numbers where it's like, I had an example where it was like P00000001, and then they had P000002, and P, right? Those are examples where prefix encoding will kick in because the front bits all match, right? And then only does the end have to be different. And I'll have more detailed examples on these. The next one is what we call offset or minus encoding, and these are very useful for things like dates and times, and not as much times necessarily, but definitely dates and numbers. That let's say you had a product number from 1 to 1,000, right? You don't need to store it in the size of a full integer. You just need to store it in a handful of bits to represent that. Same thing with dates, right? Date is a pretty big number, but if you look at it in, let's say something's an order date, so everything is 2011 or greater, well, that's a much smaller range from a 2011 to, say, 2025 than it is to store the date since the history of time. So going into more detailed examples, so pure dictionary encoding, here's an example where we're going to end up using 3 bits to store the dictionary, and in this case 0 bits for the offset because the two are always paired together. And you have dictionary values of Arizona, California, Florida, and Hawaii. In this case, assume they're equally hot because we choose to have 3 bits for each of them. And this is a simple lookup because if you have an encoded value of 011, you basically look it up and it tells you it's Hawaii, right? And so here it says the dictionary offset is 3, so 0, 1, 2, and 3. And the offset's 0, which because this is just pure dictionary, there's no offsets, and this is how you come up with Hawaii. And in this case with 3, you can do 2 to the 3rd, which so 8 possible dictionary values, right? Not enough for all the states, but maybe in your case you're talking warm, sunny vacation spots, right? And maybe there's only 8 of them in the US. So that's one example, and that's probably one of the most common ones, especially for things like states, and that you'll just use this type. I'll be back in a second. Let me see if I can get out of this. Apparently I left 2 slides hidden. we'll try that again. The next type of encoding is prefix encoding. And we talked about that at a high level, but how this will look is you have some number of dictionary bits, which says what is that front matter or the prefix, and then some number of offset bits, which is really says what's the remaining suffix. So let's say this is your data coming in, and then one we want to deal with is April 2nd. Well, you would take this April 2nd and you would look it up and you would see the front matter should be this 10, so you make that part of it. And then the rest of the bits is basically saying the next thing is a character of 2, and 2 happens to be a hex 32, if anybody knows ASCII, and so it would look like this, right? And that would be what was stored versus April 2nd, which would normally take four full characters. And to unencode it, you do the reverse, right? So this was us encoding it in. If you need to unencode it, you know that the dictionary bits is this, so then you would look it up and say it's April. And then you would know the rest of this is the offset bits. You would convert this to characters and basically, concat them on. Right? So that's going both directions to set it up and unset it. And in this case, because there's multiple prefixes that can be used, the number of dictionary bits is, non-zero, and you look up the base part in that. And you'll see it differs for the next slide. Minus encoding. Like I said, this is the one that's minus encoding or offset encoding. Here the dictionary bits are 0 because you can only sort of minus encode off of one base. So if this was your data coming in, I actually would ask why we wouldn't minus encode from like 105, but I'll ignore that. Sorry, it has to be positive. So here we're minus encoding from 100, so that's our base. And in this case, if we're trying to deal with 110, you have 0 dictionary bits, and then the question is, what is the offset? Well, the offset in this case is the 0, the 2, the 4, and the 8. So this is 10, right? So if you take your 100 base and add this 10 to it, you get your 110 if you're trying to unencode it. If you're trying to encode it, you would actually start with 100, your 110. You would take the 100 off because that's your base. You'd end up at 10, and you would go throw this in as your encoding. Right? So this is the sort of internal how all the math works. And what you'll see is, when you look at this, there are shifts and there are pluses and there are offsets into arrays. So it's very quick math operations. They're all things that can be done in the SIMD acceleration. Right? So all of these, when you have a whole page of them, you can parallelize them very fast. Right? So it's all simple operations. There's nothing, I'll call this as the no rocket science. It's all basic things getting put together so that they can be very much parallelized and automated. Does this make sense? Gives you an idea of the types of compressions we do. One of the key is today, and I'll sort of stress the today part, is column level dictionaries are static. So once you create your column level dictionary, that is your column level dictionary till we change that from being a true statement. So on top of column dictionary, there's also page compression. So what a page compression allows you to do is reduce any need to rebuild column dictionaries as new data is coming in, right? So as I talked about, numbers like product numbers, dates, those types of things tend to change as, and evolve over time. We automatically, with page compression, can still compress dates incredibly well, right? Where that doesn't work so well is, let's say you had a new product name that went from, popular things of Tickle Me Elmo to popular things of Nintendo Switch, and that tells you the last time I got to buy cool toys. So, when there's completely new characters, if they're not in the, column level dictionary, they will not compress as well. And this is actually something that is, one of the things on our roadmap is having dictionaries evolve over time as your data evolves over time. Another future improvement, and I actually talked about this already, was better compression for larger strings that are neither prefix nor pure dictionary, repeating type patterns. So, this is repeating in the middle. Things like URLs are a very common one. And like I said, it's, this is code that is in prototype mode and shipping reasonably soon in IIS, and, it's about a third of the size, especially for, this is over the whole table that was very varchar heavy. Varchar columns itself are compressing, much greater than that, but this is sort of an average. So something coming that will be in, a future mod pack. Load for column organized tables. And this one's an interesting chart that I actually pulled in that wasn't in the deck that I stole. Because in DB2 Warehouse, we are really pushing a don't use load and use the external tables with reduced logging and with all of that, because it has a lot of the same benefits with it actually being online at the same time. For 11.5, there are still cases where load will win out if you compare performance, and you could compare, especially without reduced logging, what is logged. So I think in 11.5 there will be people who definitely still use load. As we go forward and get a lot more of the DB2 warehouse, including reduced logging in, I think there will be a similar push where people will quit using the load utility and a lot more use external table loads, right? But if you use load in the initial phase, if you don't have a dictionary yet, we actually just read the data. If it happens to be a not repeatable source, so i.e. something piped, we'll actually read the data and store it. Build the dictionary, and then actually do a second pass of a load phase where we either read the import source again or read the cached version that we kept. And at that point, convert it purely into our column organized data, build a synopsis table, the user table, and all the index keys. Right? So the key here is we very much, phase 1 is analyze and build the compression dictionary, and then phase 2 is load. So for people still using load, right, one of the strong suggestions is use sufficiently large amount of representative data in the first load. Right? Can we look at the first 128 gig? Make sure that represents your data, and then you will get a very good dictionary. Large util heap, because that is, and it happens with automatic, but that lets you create large dictionaries and histograms. You can consider pre-sorting, right? Because this will actually help get a good synopsis table, right? And it potentially even pre-sort on multiple dimensions. Because the loads are offline, you can manually build dictionary and then load and insert data separately. There's some examples in the notes of some best practices. New in 11.5 is external tables. George mentioned this, I mentioned this earlier, but super fast parser, right? Lets you load CSV files, whatever format, and I think I have the same slide. But when paired with the faster insert, update, delete performance, paired with parallel insert updates, because I've talked about all these in previous slides, and paired with the vectorized insert, update, delete, and we went through this in the previous ones. I'll pair all of those together, plus this one, which is future. This can actually outperform the load utility, and it's online. So I will say this is the future for loads going forward. 11.5 is not totally there because of the reduced logging, but it will get there as long as you are in a scenario where you're okay not having a database that can be roll forwarded, or if you roll forward, that table is left at an older period of time. I have a question for that. So who uses roll forward on their warehouses versus a rebuild based on drop it at a point and then just redo yesterday's loads? So who uses roll forward? Okay. And who does I take basically an image daily, but then I can just redo yesterday's load scenarios?
We have both scenarios.
You have both? Okay. Which is why this was not free for us to put into 11.5, right? We got to make it switchable because there was some people in Camp A and some people in Camp B and some people who do both, right? So, you want to have the tables where you can turn it on, where if you were to have a failure, you either don't care about the table, or you can reload it based on a backup in, a Delta file, or that, you have roll forward for the ones that you do need it for. Automatic dictionary creation. So this is, if you are going for the method I was just talking about, where you use external the external table loads, or any insert, right? When you start inserting data, you actually get a default dictionary, and just consider that to be, it is somewhat useful, but is probably not what you want for great. And so the majority of your data is going in uncompressed. At some point, your insert data triggers a threshold, at which point we build a dictionary. Then after that dictionary successfully builds, all new data going in will automatically go in compressed and encoded. So anything before this is built uncompressed, anything after this is built will go in automatically compressed and encoded. I'll sort of basically say the automatic dictionary creation, there's technically 3 types. I'll really just focus on one. And that is the vectorized one. So much like when I talked about how we vectorized basic insert, update, delete, we also vectorized the creation of the dictionary. So, we actually work a column at a time, build it, scan it, do things much more faster. It's also much better for cache lines, much better for reads, less memory used at once. This one, really, the key summary of this is if you bulk insert to an empty table, one of the key things is we, as of 11.5, will insert much more rows, and I talked about this a little bit earlier, such that you have more rows to be able to build a better dictionary. And because we can groom them to compressed after, the fact that we waste a little bit of space at the start putting in ungroomed stuff and a little bit of CPU to regroom them later, you get a much, much better dictionary. So it was 8,000 in 11.1. If you just put in 8,000 rows and hit commit, you would have got a dictionary. Now it's 500,000 per MLN. So it's much larger, much better quality dictionary because of that. And it's also closer to the scale of load looked at 128 gig, right? You can calculate what 500,000 rows is, but it could be in that range, could be smaller, could be bigger, depending on your row length. So, so this is the example of you're inserting uncompressed. Your ADC is triggered here. There's actually rows that are still getting inserted in the meantime. And then you get compressed. Then what happens is, I call this grooming, but other people call it automatic reorg recompress. You now take all of this data and compress it so it's only this big. These extents are now marked as free, right? Because they're totally empty. As I said, there's a much higher threshold now. It allows you to build a better index. And these, at this point, once the automatic recompress comes through or the grooming, these are only marked free, right? There are still other steps required to have them actually physically freed. So the next step that would come in, and it's also automatic, and we talked about this in configuration, is as long as you have not turned it off, right? Automatically, we will once in a while check how full a table is. We will see that there are empty extents, and it will run a reorg extent reclaim. So at this point, when this runs automatically, it will go through and find every extent that has 0 rows and free it back to the table space. And like I said, as long as auto reorg config is on, this happens automatically, and that is automatically on with set workload equals analytics. So this is back to the sort of set it and forget it, or the load and go mentality in BLU of all of those things have happen naturally. So the one disclaimer to that is that will free it back to the table space. It does not free it all the way back to the operating system. So if you had 2 table spaces and you reclaimed and you want to use it by the other, there is a manual step, and that is to run the alter table space reduce max. And when I talked about extent reclaim for pure scale, you all kind of smiled and nodded, so I assume you all know what this is. Just for an interesting, part of the reason I think this is not automated is part of that sort of load and go simplicity is like with Db2 warehouse and an IIS, by default you get 1 table space, right? So technically you don't need this because you only have 1. So I think it's part of the reason it's not automated. The next slides, we'll see how I'm doing for time. Not too bad. Measuring compression. So how do you know what compression looks like? So N pages, F pages, and M pages. So N and F pages, everybody know what they are? You've seen them a bazillion times. If you're new to BLU, and because I don't think this exists for row, M is for metadata pages, right? So I'll sort of show you a bit on the next page. And then the other thing is in min tab get info, you've got your object size for the column object, but also the object size for the data object. And I'm just going to scroll to the next page. So In column organized table, you get a column object, and off the top of my head, I don't remember which type number it is. It's like 8, I think. And that's your end pages, because this is where the bulk of your user data is, plus potentially empty pages. But you also have a .dat, the equivalent to what would be the .dat in the old SMS world, or your type 0. Everything in there is essentially metadata, right? It's your dictionaries, potentially some of your, no, you'll get a separate lob metadata. And so this is called M pages for columnar. This is your end pages. Note that it does not include your empty pages. So if you have a super small object with like say you had 1,000 rows, 1,000 columns, you would have 1,000 extents even if you only had 1 row in it. And 3 out of those 4 pages would be empty, right? So it would basically show that this was 1,000 pages big even though this was 3,000 pages big. So how do you do your calculations? Well, user data is equal to the column object, the size of that and the physical size. But the whole thing is your user data plus the size of your metadata plus the page map and unique indexes, and I would also argue put your synopsis table in here. And the warning here is, as I said on the previous pages, is end pages only actually used pages. If you have super small objects with tons of columns, you may actually have a lot of space wastage due to the free pages because you chew a whole extent for every single column. So you can look at these and do a quick calculation, which is, of course, on the next page, not on this one, which I'm just going to jump to, where you can do your compression ratio as the uncompressed size divided by the compressed, right? So it's the 1 minus the page saved divided by that. Now going back to this is a great reference if you're a row organized customer. These are the stats that exist for row. The only one that is valid for columnar is the pages saved, right? And the next one is the percent encoded in the syscat columns. So you want these high. Will they always be high? No, because there's certain columns that may not compress well. But a key is that this is the percent that is encoded. It is not a compression rate, right? So if you had something that is normally 10 bits and it compresses to 2, right? At 100%, you're saving 80% of your data, right? If you had something that is 10 bits and compresses to 9, well, you're really only saving 10%. So, it is not a measure of compression ratio. It is measured about how much is encoded. Here's an example of a real-life table, and I can explain why some of them are good and some of them are bad based on the type of compression algorithms we talked about, right? So here you have a column called product info. It's a varchar. It's 40 length. There's high variance in it. And the compression ratio was 1, and the percentage encoded is 30, right? So 30% of the row were really duplicate type things, right? Reoccurring strings, reoccurring names. So you could encode 30% of it. That's not really a great ratio, but for a varchar column, that actually may not be bad depending on what your data looks like. A comment field where people write whatever random things for 600 characters, I would actually say 10 was higher than what I was expecting, right? But, maybe somebody has, it's a report card, so it says good job, or, a lot of simple things and then a lot more detail. Here's another example of a varchar, right? This is code, so this is probably like, you see very low cardinality. There's only really 4 options for it. 98% encoded, right? Here you have a customer number. Although the cardinality is still pretty high, you probably have common prefixes, or this is where things like either prefix for the varchar or potentially minus encoding if it was a numeric would kick in, right? So here you once again get very good encoding. So this is where it's good, given the types of algorithms we do for encoding, to sort of see if that matches what you're getting. We are adding new encoding algorithms, as we go, and we've added the number along the way, with the newest one coming being just a I would say an LZ compression across larger strings. Maximize, here's just a few pages of hints and tips, and other than that, I think I'm mostly done, which is good because I'm probably I'm going to claim I'm 24 minutes under or 6 minutes over, depending on which times you go for. But so, as I mentioned, your column level dictionaries may become less representative. Because of that, you might see percent encoded decreasing. And right now your option in some of these cases is having page level compression kick in and help you out. The other option is you can choose to rebuild the dictionary, and we are working on future things to allow for evolution. I think I just suggested those, so these are your unload and min move table. There's some more options in here of how to deal with such situations. I think this is the last slide. Space usage overhead for small to medium tables. So I've talked about this in 2 or 3 slides, but if you have a bunch of columns with one row, you will have a whole extent where maybe you have 1 page and 3/4 of it's unused. So the amount of wasted space can be fairly high. You actually multiply that out by wasted space in the synopsis table because it has 2 times the columns of the base table. So one of the recommendations, this recommended actually dropping extent size. You can also drop potentially page size. This is one of the examples where I would argue that the load and go simplicity isn't there, and I won't say this is. There are like the dictionary evolution, the better compression are probably higher on our list, but this is one of the ones we're thinking about alternatives.